Welcome to the third online lecture of CSE 4551 Computer Graphics and Multimedia. This is part 2 of the topic we were covering in the previous lecture, that is ray casting and rendering. In part 1 of this lecture, we had finished up to cameras and we had seen some differences between orthographic and perspective projection. That is, our topic was up to perspective and orthographic. Okay, so today we had also seen how we can represent rays using parametric line equation. In order to find the intersection of that ray with a plane surface, we need to formulate a representation of the 3D plane as well. That part will be started from today's lecture. Before we have seen that parametric line equation was defined as ET equals R0 plus TRD, where RD was the unit vector along the direction of the ray, and R0 was the origin point, and this ray representation was an explicit representation. Now we are trying to find a representation of a 3D plane. An infinite plane can be defined using a central point that lies on it. In this case, we are defining it as P0 equals x0, y0, z0, and the normal vector as n equals a, b, c, the three components that will describe this vector. These are the two quantities that we need to define a plane. And the implicit equation of the plane would be HP equals ax plus by plus cz plus d equals 0, and this can otherwise be written as the dot product of n and p plus d equals 0. Here n is the normal vector and p is the any given point x, y, z. And what is d? D is basically, d can be found as ax0 plus by0 plus cz0 plus d equals to 0. This particular thing should be equal to 0 because since p0 lies on the plane itself, so putting p0 on the left hand side should result in the right hand side to be equal to 0. So d should be equal to then minus ax0 minus by0 minus cz0. And for any general point p, we will have that h of p will determine the distance of the point from the plane, given that n is normalized, and it is a signed distance. That is, if h of p is greater than 0, then p must be above the plane. If h of p is less than 0, then the point p must be below the plane. And for all points where hp is equal to 0, those points must lie on the plane. Okay, now we move on to explicit and implicit equations. Since we already said that the previous ray representation that we did was an explicit representation, and now we are saying that the plane representation was an implicit representation. So what are we need to notice the differences between explicit and implicit equations. The ray equation we talked about, that was an explicit equation, and the plane equation is an implicit equation. The three characteristic differences between these two types of equation can be seen here. These are the three main characteristics, but the main point to note here is that explicit equations such as these can be used to generate points. For example, here putting different values for t, we can have different points, different values on the right hand side, and these will create different points. So this has the capability of generating points that should be on this ray. On the other hand, implicit equations like this, they do not generate points. They only verify whether a particular point is on that plane or not. We could actually have the reverse, that is explicit plane and implicit ray. And how that could be done, you can actually check that out if you want. But in essence, both can actually represent the same thing. Both explicit and implicit equations can represent the same thing. The reason we are keeping the ray equation as explicit and the plane equation as implicit is because we need the next section will make it clear why. So we need to actually perform ray plane intersection. We need to see whether the ray coming towards the plane actually intersects with the plane or not. So for that, we actually need to that would mean that both equations must be satisfied for that particular point where the intersection occurs. And for that, we can actually find that intersection point by putting the explicit equation of the ray into the implicit equation of the plane and then solving for t. You can actually see the steps here what actually occurs. What we basically did here was, in the equation, implicit equation of the plane, we just put p, we just replaced p using the right hand side of the ray equation, and after putting it we found that t should be equal to minus d plus n dot product with r naught divided by n dot product with rd. Here r naught was the origin point and rd was the unit vector along the ray's direction. So what will happen if n dot rd equals to 0? We will have a division by 0 here. So what does it actually imply, division by 0? Recall that division by 0 means this whole thing will result in t to be infinity. So that means that the ray would meet the plane at infinity. Since the plane and the ray are actually parallel to each other and they can actually never intersect. So that is why t would actually come as infinity here. For this reason, we actually need to handle this case separately. For this case, we basically will never render this particular plane. This will happen when the ray comes not in this direction but along the edge of the plane. When the ray comes along the edge of the plane, uh, only then we will have n dot rd equals to 0. Here n was the normal vector and rd was the direction of the ray. And when will n dot rd be equal to 0? When will the dot product be equal to 0? When these two vectors are perpendicular to each other. And these two vectors will be perpendicular to each other when the ray's direction is along the edge and the plane's normal is coming in this way. So that's when they are perpendicular. And this means that this particular plane should not be visible when the ray is passing along this direction, right? So that is what n dot rd equals to 0 will imply. So instead of having a division by 0, whenever we have a division, we have n dot rd equals to 0, we'll simply not render this. We'll not even perform this calculation because the processor cannot handle some logical errors like this where we will have division by 0. Okay, and we also need to render the object that is closest to the camera. So for that, we need to verify that the intersection point that we just got, the t value, is less than the t current. Whenever we find an intersection point, this should be less than whatever current t that we are considering, the most recent t that we are taking. And we also need to verify whether the object is within the eye limit or view distance by checking that if t is greater than t min. If it is, then we don't have to render it since it is beyond our view distance. Those who have played FPS or open world games before may have noticed such a thing in the graphics settings. There is a separate option for tweaking the view distance, which requires more powerful hardware for setting it at a higher value. And you can already guess why it would need more resources for setting it higher. That is because the game engine would have to render objects that are farther away from the player. That means more and more objects would need to be rendered. We know how the intersection of the ray and with the surface will cause it to get rendered depending on whether it is closest to the camera or not. But how will the shading be done on the surface? If the shading is done uniformly, that is if you have a solid color for the whole surface, then it will not look 3D. So the shading of the 3D objects cannot be uniform. There are various types of shading, but the most common one is diffuse shading, which uses the dot product of the light direction and surface normal. If the direction of light is parallel to the surface normal, then it gets illuminated most, and otherwise the illumination varies in a gradient based on the dot product value and is clamped to a minimum of 0, which means full shadow, so that there is no negative value for illumination. You can actually make it analogous to a ball. If you put a ball here and the light is coming in this direction, then the part of the ball where the surface normal is along the direction of the light will get illuminated most. So that part will be shaded with maximum luminance, and the part of the ball where the surface normal will be at an angle to the light ray will be shaded differently, will be shaded dimly. So the illumination will be less there. And similarly, the part of the ball that is on the opposite side of the light ray, that will be shaded with even less luminance. That will be inside a shadow. So this particular effect will come based on the surface normal, what angle the surface normal makes with the direction of the light. So the dot product between the light and the normal will be used for shading. So next we go for sphere representation. We have already talked about plane representation and how the intersection of the light ray with the plane would be done. So now we uh, see an example of how a curved surface such as a sphere gets rendered by calculating the intersection of a sphere with the ray. For that we need to represent the sphere at first. So just like we defined an implicit equation for plane, we can also define an implicit equation for a sphere as HP equals p square minus r square, or in other words p dot p minus r square equals 0, assuming that the center is 0 comma 0. We actually can remember this from our intermediate level coordinate geometry, where sphere was actually defined as x minus h whole square plus y minus k whole square equals to r square. Here x, since we are considering the center to be origin, so this is the simplest sphere that we can get. So next we need to know what this ray sphere, how the ray sphere intersection will work like. Similar to what we did with the plane equation, we will simply put the explicit equation of the ray into the implicit equation of the sphere and solve for t. So basically what we'll do is replace p with the right hand side of the ray, and then we'll get this particular step, and then when we multiply this we'll get this final result. So this is basically a quadratic equation of t, since as you can see we have highest power of t is 2, then power of t is 1 here, and there is the power of t is 0 here. So this is a quadratic equation of t, where the three coefficients a, b, and c can be written as a equals rd dot rd. This is more easily seen from here. A equals rd dot rd, which can actually be written as rd magnitude times rd magnitude times cos 0, and the magnitude of rd is equal to 0. How do you know this? Because rd is basically the unit vector along the direction of the ray, so the magnitude of rd must be equal to 0, must be equal to 1, sorry, and this is 1, this is 1, and cos 0 is equal to 1, so the whole thing is actually equal to 1. And b here is 2rd dot r naught, and c should be equal to r naught dot product with r naught minus r square. So we have these quantities here. We have to recall some algebra knowledge from intermediate level to know how the discriminant formula comes. D equals root over b square minus 4ac, and so the solutions of the root will be t equals minus b plus minus d by twice a. There can be three cases here depending on the signs of b square minus 4ac. Case 1 is b square minus 4ac is less than 0, then there will be no intersection. That is because root over a negative number will be an imaginary number here, so that would mean that the value for t, that will not be a real value, so we will not have any actual real intersections. This is an example for the first case, and the second case says that b square minus 4ac is equal to 0 exactly. Then intersection will be found at exactly one point. Since this plus minus d will become 0, so there is no plus minus term, there is no chance for having two different values. We will only have one value, which is t equals minus b by twice a. This is an example for the second case. And b square minus 4ac is greater than 0, then we will have two different intersection points, and these two intersection points can be seen for this example for case 3. Okay, now we move on to constructive solid geometry. What it says here is that constructive solid geometry is a neat way to build complex objects from simple parts using Boolean operations. In other words, this is basically a technique for creating complex surfaces or objects by combining simpler objects using operations like union, intersection, subtraction. We have all used AutoCAD before in our first year labs, and there we already saw a use of this technique, but maybe we didn't know the name at that time. So recall how we used to obtain complex shapes by performing union, subtraction, and intersection of one shape with another. You can actually see this slide for a simplistic example. but a more realistic example can be seen here, where having a cube and a sphere, we can create shapes, a complex shape like this by combining them using union, or we can perform subtraction of the cube from the sphere. What we are doing here is we are subtracting the sphere from the cube, and here we are finding the intersection of the cube with the sphere. So in this way we can find some complex shapes from simple geometry, primitive shapes like cubes and spheres. Okay, so now we try to find out, we try to think how this particular technique of CSG can be implemented for softwares like AutoCAD. There can be 4 cases here as shown in slide 49. So this is slide 49 and you can see 4 cases here. First is that there are points on A. If you consider 2 different spheres A and B, there may be points on A that are outside B. There may be points on B that is inside A. There may be points on A that are inside B, and there are points on B that are outside of it. So these are the 4 cases that can happen. And here we also need to find, in order to implement CSG, we need to at first register the points at which the intersections will occur. We can actually do that using the figure of slide 50. According to this, here the intersections occur at these particular points. The red points denote that the intersections occurred with sphere A, and the blue points show that the ray intersected with sphere B. And these intersection points can be found using the techniques we discussed before in ray sphere intersection. And after these intersection points are found, we can proceed in 2 ways. We can test the inside intersections. We can find the intersections with A and test that whether they are outside B or inside B. For example, these 2 points are outside B. This is inside. This is outside B, but this is inside B. Again, these are outside B. Similarly, for B, we can find intersections that are and test whether they are inside or outside of A. For example, this is outside A, but this is inside A, and these 2 points are outside A. This would certainly work, but we would need to determine points, whether the points are inside the solids or not. In both cases, we will have to check whether each of the points are inside another solid surface or not, which is pretty cumbersome. So we move on to a different approach, which is checking overlapping intervals instead of inside intersections. Here, what we do is that we check whether we keep an entry bit and an exit bit for each intersection. That is, and we can know whether this was an entry point or an exit point by checking the angle that the surface normal creates with the ray direction. If the surface normal creates obtuse angle with the ray direction, then the ray goes from outside to inside. And for example, if the surface normal was like this and the ray was going in this direction, then the angle here would be an obtuse angle greater than 90 degree. So that means that this was going from outside to inside. And here, when the ray goes from inside to outside, here the surface normal would be like this. So the angle is less than 90 degree. So this means that it is going from inside to outside. By checking the angle, we can actually know whether we should put an entry marker here or an exit marker here. And then in this way, after finding the intervals, we can actually compute union, intersection, or subtraction of the intervals very easily. And thus, we can create complex shapes from simple shapes like this. Okay, so this will be the end of the lecture on ray casting and rendering. Thank you for your attention.